Keshav, you are invited to give us your presentation, which is basically on the project that you are working on and coming fairly close to completion here at IIT Gandhinagar under the HOMI project.
Michelle, one quick thing, Keshav needs an introduction. So why don't you do that? Being the first speaker today.
That is true. That is true. Keshav, I'll introduce you from memory, Keshav, because I cannot even list all the BSc and MScs that you have under your arm. I will simply say that you had a traditional education in a Gurukula, and you are very strongly rooted in Sanskrit. You have a degree in Sanskrit also. And then you did your PhD in history of astronomy under Professor Ramasubramaniam at IIT Bombay. That is precisely the small cell, one and only cell of its kind that I mentioned earlier. And this was on a text of the 17th century, Jagadbhūṣaṇa by Haridatta. And now in your postdoctoral fellowship, you are amplifying upon this work and preparing an annotated critical edition, and hopefully looking into the mathematical methods, algorithms in particular, that he used in constructing the tables that are in that text. So I hope I've done justice to you, and yes, you can add any further details that you wish.
Thank you very much, Michelle, for the introduction, and good morning, one and all. So today I'll be speaking on a glimpse of an astronomical table text, Haridatta's Jagadbhūṣaṇa. During my PhD at IIT Bombay, we had a preliminary understanding of the whole text, and as part of it, we gave the translation, and we brought out a critical edition, and up to some degree we also brought out the mathematical methods and astronomical ideas from the text. And now at IIT Gandhinagar, we are mostly focusing on the commentary, where we completely deal with the mathematics and the tables and their application to a larger degree. So before going to the topic today, I just want to share you this quote. This is from a paper by M.D. Srinivas, The Untapped Wealth of Manuscripts on Indian Astronomy and Mathematics. So there they mention that even though there is amount of source in Indian astronomy and mathematics, only a marginal amount has been studied so far. As we can see, only around 150 texts were edited, and just about 30 texts translated during around 150 years. And then during the last 70 years, another 300 texts have been edited, and only 66 texts have been translated. So this shows that a lot of untapped wealth is still there, and we need to study it and publish it and circulate it. So why I'm sharing this today is that because this is a young scholars conference, and I hope many youngsters might have joined by now. I can see around 64 participants. So especially in this field, when we start researching or when we start studying, we sometimes stumble upon the sources that we might not find, we may not understand. So, but there is substantial amount of material, and we just have to consult the experts and start our research and studies, and then contribute to the field. So, out of these, there is a large section of material available in table text genre. So, as we know, mostly we can classify the astronomical and mathematical texts into three categories: Siddhantas, Karanas, and Tantras. But there is another section called Saranis or Koshtakas, so which is basically tables, and we have an attested text with that to get some instruction and guidance how to use those tables and apply them. So this observation has been made by Professor Clemens Montel and Professor Kim Profker in their book Sanskrit Astronomical Tables. So they say that out of these 9,000 source materials that we have, around, say, even if we say 1/4 or just 1/2 of these texts, then that will be related to the tables. So it can amount to at least thousands, if not 10,000s. So there is a lot of material available for the study. So today I'll be speaking on just one such table text by Haridatta, and let's have a look at the author. Very little is known about this author. So very few things like the place from Mewar, and we know his father's name, Haraji, and he also mentions in the colophon that his father was one of the reputed mathematician of that time, and his exact date of birth is not mentioned, but we assume that he was there in the 17th century because the text written was on 1638 CE, and his patron was Jagadbhūṣaṇa. He belonged to Sisodia clan, a Rajput clan in Rajasthan, and his only work that is available today is Jagadbhūṣaṇa. The text Jagadbhūṣaṇa, it is, as I told, table text, which means it has a text of 5 chapters, which will explain how to use the tables of Jagadbhūṣaṇa and how to prepare one's own calendar, almanacs. So it has 131 verses and a set of prose, and it has a 21 tables set. So there are 21 parameters, including lot of the year, epoch, so on and so forth, and also the planets and their planetary phenomena. But the substantial amount of tables, so total amounting to 500, exist with the text. And the epoch chosen is 1560 Saka, as we see. So in Put Sankhya, he says Purna Sharendriyendu plus Chandra. So that will be 1560. And one striking feature of this Jagadbhūṣaṇa is that the encomium. So basically, he praises the patron and his lineage, the Jagadsimha and Sisodia clan, beginning from Surya Vamsha. So he says that this clan belonged to Surya Vamsha. So from there it originated, and we see this very rarely in astronomical and mathematical texts that such a poetic skill has been displayed by an author. So I'll not go into detail. He used different chandas, prosody, and alankaras, figure of speech. So this text seemed quite popular because it survived in more than 20 manuscripts in different libraries in India and also abroad. And this is catalogued by Professor David Pingree in his very famous work, Sanskrit Astronomical Tables in the United States. But for my research, we could obtain only these 10 manuscripts, where 3 of them give the text only, and other 7 will give you the tables. So today in this talk, I'll be focusing on 2 technical aspects. One is the cyclic periods mentioned in the text, and a simple solar table, how we use it, how we decode it, and how we understand it. So here, as we know, the chakra basically means a cycle, a wheel, a circle in Sanskrit, but it is a technical term used in this particular text. So here it denotes a cyclic period measured in years, in which planetary phenomena repeat in almost the same background of stars in the next cycle. So we know that every revolution, the planet will make one complete revolution 360 degrees. But the planetary phenomena, that for example the helical rising, that's Udaya and Asta, and Vakragati, Vakragati and Nijagati, that is retrograde motion, this may not occur in the same background in the next revolution. But we fix a period called cycle or chakra, where it almost repeats in the same background of zodiac signs. So these are the associated cyclic periods for Lord of the Year. It's called abdapa, 89 years, and epact, that is Shuddhi, 122 years, so on and so forth. And this is the yearly increment. So that is, so what is the change in this particular parameter at the end of solar year? So this is in days, and epact is in tithis, and longitude of the moon is in degrees and also degrees. So here we can see after 89 years, for example, in this case, a very small amount is remaining, very small amount. So he'll also give the corrections to incorporate this small discrepancy, so that the same table can be used for the next cycle of 89 years. So these are the cycles of planets, and we can see a very interesting fact here, that these cycles, or the idea of cycle, has been borrowed from Babylonians through Greek astronomy, and then Islamic tradition, then Indian tradition. It was not, we don't see any evidence that these cycles were used by earlier astronomers and mathematicians in India. And we see mostly resembling figures here, except for Jupiter and Venus, because we can definitely take different cyclic period, and we can also do proper correction terms so that they can be rectified. So today I'll only talk about one particular parameter, that is Lord of the Year, and how it is actually used. So first we need to know that the sidereal year fixed by earliest Siddhantic text is 365, 15, 30, so on and so forth. And Bhojaraja in the 11th century gives a correction based on the latest observation and other mathematical tools. Then the corrected value of the sidereal year that we have is 365, 15, 31, 17, 17. So now what is abdapa? Abdapa is basically a day and quarter remaining after eliminating the integral avadhis. So one avadhi is 14 solar days, and the last one is also considered as avadhi, because this is especially used to find out the amount of the value of abdapa. And in Sanskrit we know abdapa is abdam patiti abdapa, so the Lord of the Year. So when we multiply this parameter by the cyclic period 89, we find this small residual. This is in addition, and that is given in the verse Gobinjaraha Varshapateshcha Chakram. Chakram is a cyclic period. Then how to rectify it? Cyclic correction is given in another verse. Gadani Chakrani Bhajet Vivedaihi. In case of Lord of the Year, we have to divide 1 by 42 and add it to the cycle of 89 years, so that the next cycle of 89 years will have the same values that we can see in the table. So this is a table of Jagadbhūṣaṇa. Here the first row gives the argument in years from 0 to 88, and these are the values of Lord of the Year. Okay, and if we take mod of this value, we'll get the weekday. So we can see this oscillating between 1 and 6, sorry, 0 and 6, the values. So here why these tables are actually computed and provided for the users. Basically, to simplify the calculation, and we can directly use these tables for just single lookup, and we can prepare our own calendars. And the second topic I want to talk today from Jagadbhūṣaṇa is how to find solar longitudes from the tables. And this is the famous equation for equation of center that we know based on the epicyclic model of the planets. So I will not go into detail. Here we have two terms. So one is the measure of the epicycle, and the other is the apogee and the mean position of the planet. It can be sun, it can be any other planet. But in terms of sun, we only add the Manda correction, not the Shikhara correction. That is equation of center. So when we have the mean longitude, we have to add this Manda Phala, that is equation of center. So we'll get the true longitude of the sun. And these are the different values from different texts, Siddhantas. And when we plug in these two values, this is solar apogee and this is Manda epicycle. In this equation, we will find different values. So Haridatta is the follower of Brahma-Bhaksha. So he used those parameters accordingly. Here we see that the first row will give you the argument in avadhis and also in days, from 1 to 27 and from 0 to 364 days. And this is the true solar longitude. Okay. And then we have the gati, that is the true daily motion in that particular avadhi of 14-day interval. And we have Gatyantara. With the help of Gatyantara, that is the difference in the values in this row, we can use it for interpolation method to arrive at any given day between the avadhis. And this is tabulated here. So after obtaining the true longitude of the sun, we have to apply certain correction for different observers having different longitudes of meridian and different latitude. So Deshantaram, Phalam, Yatam, Charam, Bhuja Phalam, Tatha. So these are the 4 corrections. And Haridatta right away gives these values computed for Ujjain's location with the roughly 24 degrees latitude, and he gives Deshantara table empty. It is completely empty because this is not applicable for Ujjain, and only with different meridian one has to compute his own Deshantara, and then we have Trayatyam. We have to add algebraically the Yata Phala, the Chara, and Bhuja Phala. Then we have this. This has to be added to the true longitude of the sun. Now it's just tabulated here. These are the 4 corrections. Deshantara correction. So I will not explain these corrections, but I'll directly go to the tables given by Haridatta. So this is Deshantara correction, basically accounting the distance in longitude from Ujjain. And this is Bhujantara correction. See, Bhujantara and Udayantara are basically 2 components of equation of time. One is due to eccentricity and the other one is due to obliquity. And these are the equations, and we have to add this particular Bhujantara correction accordingly. So this is in my study we provided this graph because we have to sometimes verify the tabulated values. There can be some typo, there can be some scribe error, there can be sometimes mistake in approximating. So we just have to verify with modern sine tables or modern calculators how far this is accurate. So as we can see, this is Bhuja correction computed versus Bhuja correction given in the Jagadbhūṣaṇa, we find fairly accurate values here. The same way Udayantara correction, we also find very good accuracy here. And Cara correction, another one. Here we see it is very accurate in terms of the value given in Jagadbhūṣaṇa as compared to the modern values. And now we have to see whether to apply Trayekyam, that is the sum of these three, or the Chatushtrayekyam, sum of the four including Deshantara. So for Ujjain, we have to add only these three corrections. And for any other longitude, we add the fourth correction, that is Deshantara, and we arrive at the corrected longitude of the sun. So these are the longitudes given in Jagadbhūṣaṇa, and these are the correction terms, and in degrees. When we add these with true sun, we'll find corrected true sun. So this actually simplifies the calculation from the author, for the users of these computational methods, so that they can generate more and more such calendars, almanacs for different locations and different times. So some concluding remarks. Astronomical tables come very handy while preparing the almanacs. A huge scope exists in studying this particular classification. Understanding of these table texts will also give historical details such as the transmission, the development, new methods, and the direct acquisition, etc. Thank you very much.
Thank you, Keshav. Very compact presentation, and of course very technical because the issues involved are technical. We'd like to have comments. I may ask you a very simple question, perhaps, to help those not so familiar with this field to understand exactly why these long cyclic periods at all. Because, for example, modern astronomy is not bothered by such long periods. What practical purpose did they serve? Can you just clarify that, perhaps?
Yeah, so to be honest, we didn't actually dig into that particular aspect, but we can assume. It is not mentioned anywhere in the texts or the earlier studies, but we can assume that every astronomer or calendar maker, for their own time and place, they had to use very complicated Siddhantic methods where they involve very large parameters, because in Siddhantas we start the calculation from the beginning of Kalpa. There's no shortcut. So then we had tantras and karanas to simplify that computation. But still, you will be calculating for example, if you want to find out the solar longitude for every day. So you have to use sine tables to compute for every day. But when you have already tabulated values with you, and maybe I think in the 17th and or 16th century, publishing or copying these manuscripts was not very difficult. So they used to prepare long tables so that it is easily accessible. As we have seen, Jagadbhūṣaṇa tables are available in almost 26 libraries. So for any calendar maker, it may be very easy to just borrow the tables and prepare a calendar for its time and place. So that is, we assume.
Thank you. I failed to mention that you are closely supervised, even though you sit here at IIT Gandhinagar, and we keep in touch with you, and we know what you are doing. You're closely supervised by Professor Rama Subramaniam and Professor Clemency Montes. So, remote supervision, and this I should have mentioned at the start. Now we would love to have some comments, maybe from the scholars first.
Hello, okay?
Yes. Yes, Professor.
Yeah. Keshav, would you So is it that many of these tables are all only theoretical tables? You see, that is, they are using some, Tantra text or even a Siddhanta text, okay, for their calculations, and they are only giving the calculated values, not some observed values or things like that.
Yes.
Am I right
Yes.
in saying that?
Yes, sir, you're absolutely right. They completely use the methods given in tantras and karanas. For example, here Haridatta uses mostly the Brahma Paksha, this Brahma Paksha tradition, and also the computations given in Grihala Ghava, for example, and Karana Kutuhala. So more or less, we find the method used by Haridatta is from Siddhantas, Tantras, and Karanas. So we don't see any like observed data in these tables.
Yeah, one more remark kind of a thing. You see, you were talking about the periodicities, various periodicities, planets and things like that, okay? See, if you consider my sun and moon, for instance, that is the simplest actually. See, it's true, 248-day cycle was there, at Babylonians were there and the Greeks had and all that, and Indians might have borrowed that, but I think they carried it forward quite a bit, and which may not be there, and that is my impression. I don't know. I'm not so well read about this Babylonian Greek astronomy and all that. See, for instance, Karana Paddhati, it makes a theory out of it. I mean, theory of continued fractions, to find out the Andadina, Anvid anomaly, zero, and with many other things, and give a systematic procedure. Okay, and Madhava, for instance, gives the procedure to find out the longitude, true longitude of moon at 9 instants during a day. You see, and this involves some theory using the Kuttaka method and things like that.
Yes.
So in fact, I'm throwing this question open to the scholars. So theoretically there is some advance. Karana Paddhati. In fact, we've seen that recently in Drupkarana, a Malayalam text. Also of around 1600. So it carries it forward a little bit more, this use of continued fractions and things like that, So that seems to be maybe, somewhat characteristic of Indian methods only, using this Kuttaka method and all that and relating it to this periodicity.
Thank you, Sriram. There is a question from Professor Kim Plofker. It is in the chat. Yeah. Thank you very much for this very interesting talk. Can you say something about the expectation of calculations with sexagesimal numbers as opposed to decimal in these computations? Are sexagesimal values generally converted to decimal integer numbers of the smallest unit for arithmetic computations?
Yeah, ma'am, so did you mean the computations done by Haridatta or by us?
Yeah, I mean, certainly how we can reconstruct them is another matter, but in observing an udaharana for a text, for example, or seeing how the table values seem to have been computed, do you get a sense that there is what you might call native sexagesimal calculation? I mean, people working in the base 60 numbers, even in multiplication and division, or do we have what we sometimes see in other commentaries, just collapsing everything into an integer multiple of the smallest unit? You get a very large integer, but that's okay. With the Indian decimals, you can manage large integers. So you do the computation and then reconvert to sexagesimal. So I'd like to know how do the cyclic tables manage that?
I cannot tell for sure how actually it was practiced in the earlier times. The only way we can see that after we compute, say for example, we convert it to decimal and then calculate, and we can also build some tools or by hand or spreadsheet using the exact sexagesimal values and see at what decimal value the computed value is differing from the tabulated one. And if we see a pattern, so then maybe we can verify what was the practice in those days. Otherwise, we cannot say for sure. Thank you, ma'am.
Thank you, Keshav. There are two more questions. One from Professor Shailaja Sharma, which asks whether the use of large periods is intended to get better rational approximations.
Yeah, that is true. That is true for sure, because these yearly increments, as you have seen in the slides, that it is not it will not give any integral value, even if you multiply by 10 or 20 like that. So they find the shortest period, in fact, to find more or less integral value. You have seen in case of Venus, they have taken 227. It's very huge, and we see in Jagadbhūṣaṇa that for Venus, you will have a true longitude computed for 227 years. So this is not a simple task. So because after you multiply the cyclic period of 227 by the yearly increment, you will find fairly integral value with small residual. And for that also he gives correction method, so that this can be used for the next cycle and also the previous cycle.
Keshav, since we are running a little out of time, very briefly, can you answer the last question? Apart from astrology, was there any other practical application of such accurate astronomical calculations? Briefly.
The idea is that in the earlier times, this astrology was one of the parts of the applications for rituals, for like muhurtas, etc. But astronomy was also used for agricultural purposes. So what is the right time for sowing and harvesting? And it was used for navigation purpose, because they used to go in the seas and the oceans. For example, I'm just giving an example. So this was,
thank you. We will thank you warmly once again, and we'll close your session.